So welcome to this grand event, the defense of my PhD student Pranav Jayanti. Let me say a few words about Pranav. Pranav obtained his bachelor's degree and master's degree from the Mechanical Engineering Department of the Indian Institute of Technology in 2016 with a minor in physics as well. During his undergraduate studies, he was very adventurous. He spent a summer as a research intern at the Karlsruhe Institute of Technology in Germany. And he joined the University of Maryland, the physics department, in the fall of 2016. He advanced to candidacy in the fall of 2018. And if he doesn't mess up today, he will join the Department of Mathematics at the University of Southern California in the fall of 2022. So Pranav, it has been a very big pleasure and a distinct honor having you as my student, and the floor is yours.
Thank you for the introduction. I'm going to dim the light. Am I audible to everybody here and in Zoom?
Yes, for Zoom.
Okay, thank you. All right, so I've been here a while now, and this is the fruit of my labor, I guess. I've looked at two models of superfluidity and analyzed them, taken from the physics literature and analyzed them from a mathematical perspective, right? So before we get into any models of the models that I've studied itself, I'm going to first give you a brief introduction of what superfluidity is. So we know that the incompressible Navier-Stokes equations are used to describe fluids, and this is perhaps the most common description that's used in practical applications and also studied in theory, right? It's used to model fluids with constant density, and the standard assumption is that the shear stresses are linearly proportional to shear strain rates, which is what are called Newtonian fluids, right? And this manifests itself as viscosity or a drag force on in the large length scales. But essentially, at very small scales, this is an entropic drive for particles to exchange momentum through collisions with each other and achieve some kind of equilibrium. Right? Particles of different layers dragging each other. Now, but certain fluids are fundamentally inviscid, okay? And these are called superfluids. So in this, one would expect that the particles of the superfluid must move in unison. They should move together in the same state so that they don't have this drag between them. And this is usually achieved as a ground state of a Bose-Einstein condensate. The transition from a regular fluid to a superfluid is fundamentally quantum mechanical. Helium-4 and helium-3 are the most well-known superfluids, perhaps the most studied. They have some very curious properties, which I can maybe discuss during the question answer session later on. I don't want to get into these now, but they have some remarkable properties that classical fluids don't exhibit. So here's a phase diagram of helium-4. Okay. So we know that for any substance, when it's in a liquid phase, if we cool it isobarically, so this is pressure versus temperature. If we fix the pressure and then keep reducing the temperature, eventually the liquid becomes a solid. Right? But that's not the case for helium at low pressures, below about 25 bar. It remains liquid all the way to 0 Kelvin. There is no solid phase when you're at low pressures. And this phase here, liquid 2, that's the superfluid phase. Okay. The transition happens at around 2.17 Kelvin, and that's called the lambda point for helium. Now, as I said, above the lambda point, you have completely normal helium, and that's the technical word too, normal liquid helium. And if you go all the way to 0 Kelvin, you have what's completely superfluid helium. Between the two temperatures, as you keep lowering the temperature from 2.17 to 0, the fraction of normal fluid keeps reducing and the fraction of superfluid keeps increasing. So it's a conversion from one state to the other. Now, yeah, like I just said, at 0 Kelvin, you have pure superfluid, and this is usually very well described by the nonlinear Schrodinger equation, at least at low energies. At non-zero temperature, as we just saw in the graph, there's a mixture of the two fluids, and because only some part of the normal liquid has condensed into this, the ground state. So when we have these two fluids, it's important that we understand and characterize the interaction between these two phases, right? This has physical applications because helium is, as most of you here might have heard, it's used as a cryogen. That's its most common use, but it's also used as a solvent in certain spectroscopic analyses. And I also, while doing the literature review for this, I came across some another application of a quantum gyroscope, which is extremely sensitive to very tiny rotations. Okay. So there are applications, and therefore you want to understand all the phases and the transition between them and see how they interact with each other. Okay, so now I'm going to present the first model that's called the Hall-Winen-Bekarovich-Kalatnikov HVBK model. Okay. So normally superfluid vorticity is in the form of discrete filaments, and the circulation around these filaments is quantized. So it can take discrete values. It can't just be about anything you want, like in classical fluids. But here, this is a macro scale model. So we go to very large length scales where this discreteness is not really of concern anymore. So we assume both the fluids are classical, that this quantization condition can be ignored at large scales. And we add a coupling term that in the equations that couples the two fluids. So this model ignores vortex dynamics and relaxation, all right? It assumes this continuous vorticity field, not discretized filament structures. It's useful when there's a high density of vortex filaments that are well aligned, like in 2D flow, right? And therefore, it's been used quite a lot to study the instability of superfluid Taylor-Couette flow. A modification of this, the original HVBK equations have also been used to study quantum turbulence and figure out what the behavior of various length scales are, the scaling laws and stuff. So with that said, this is the 2D viscous model that we're considering. Now, and incompressible. So we have the divergence free conditions. N here is normal fluid, S is superfluid. So we assume both fluids are incompressible. We're considering the model in 2 dimensions, okay? And we've also considered isothermal, right? So because if temperature changes, then the fluids can convert between each other. And we have ignored that and assumed that there is a fixed fraction of each fluid in the system. Yes.
Are we able to ask questions? Is that okay?
Yeah, sure.
So I guess I have a clarifying question. So I was trying to understand the relationship between these equations and the GP equation.
Okay.
In particular, the nonlinear Schrodinger equation has some particular form. Do these equations reduce to the GP equation, or do they not? And so that's, I guess, that's my question.
No, because the Gross-Pitevsky equation is used to model the superfluid at micros. So it's a microscale model, which is actually what we're going to look at in the next thing. I should probably remove this.
Okay, so but I guess the question is, what's missing in these equations that is described by the nonlinear Schrodinger equation?
Oh, this is a large scale model.
Really
Yes.
large scale.
So the vorticity is assumed to be continuous, and you don't consider any quantum mechanical component. There's no wave function, and it's a completely classical model.
Right, but are there physics issues that go away that you actually need, even though you're describing a large scale system?
Yeah. So this, like I said, has been used to model superfluid turbulence, and because when energy keeps going down and smaller scales are unlocked, you would eventually reach a scale where you've reached like the inter-vortex separation distances. And at that point, then you have to do different kind of modeling. So it's insufficient there. So that is definitely a concern that's been raised in the turbulence literature for superfluids. So it is insufficient when you go down to small scales.
What is nu S if that's a superfluid?
Right, exactly. So I was going to address that next. So you notice that there is a superfluid viscosity here. Now this is used in all, or there's some kind of control on the small length scales or high frequencies that is required to while studying these models. Now in the literature, there are 3 different methods of dealing with this. There are some papers where they've just straight up suppressed the superfluid velocity and it's higher frequencies, the higher modes. There are some works where they have added some subgrid modeling like large eddy simulations. And there are other papers where they've used an artificial viscosity model. So here we assume this artificial viscosity. And I am going to comment a little more about this later on in the talk, but usually this viscosity is taken to be a few orders of magnitude lesser than the normal fluid viscosity. I'm going to skip this for now and come back to it later on if time permits. So now we have a system of PDEs that I just presented, the HPBK model, and our goal was to see if we can establish well-posedness for this. So whenever you have a PDE, you want to know well-posedness, which is solutions, do they exist? If they exist, are they unique? And are they continuously dependent on the initial conditions? So if you change the initial data by a little bit, do the solutions also vary by a little bit, or do they vary by a lot? Right. So so we were able to establish well-posedness for this system. And the word global here is global in time, which means the solutions exist, are unique, and are continuously dependent on the initial data for an infinite amount of time. So the main points of the theorem are that if you take divergence-free initial conditions, UN and US, that are in this function space HM, which is the Sobolev space of order M. So the mth derivatives of these velocity fields are square integrable, right? That's what HM is. Then we can show that there exists unique strong solutions, and this solution map is Lipschitz continuous, which means that they continuously depend on the initial data. Okay. The analysis to prove this result borrows from the standard Navier-Stokes theory, but we also have to deal, obviously, with this coupling interactions, right? And once we show the idea here is to first establish local well-posedness of the model, and then extend or continue the solutions from local existence to global existence. And for that, we derive an analog of the famous Beal-Kato-Maeda theorem in Navier-Stokes theory. So I'm going to give a quick sketch of what this proof looks like.
Sorry, can I ask another one?
Yes.
I presume this all fails if you set the viscosity of the superfluid identically to 0.
Right. Now, I'll comment more on that in a bit. Yeah, all the issues with the viscosity. So we look at this equation as a perturbation of a heat equation. So we try to solve this system for a map phi t that depends on t and on un. We fix us, okay, to be something, and then for un we try to solve this map, and we define a certain norm. It's not, I put it here, but it's not really necessarily what it is. We define a norm. Let's call it xn. So there's a space xn defined by this norm, and our idea is if you plug in a un here, you get a value for phi by solving this equation. Then you take that as your next approximation, so to speak, put it back in this equation and get another value of phi. Put it back and get another value. You keep iterating this procedure, okay? And you want to show that that iteration actually converges onto something. That something is what your final solution is. So in order for a convergence to happen, in order for this scheme to work, you need to basically show that this map phi is a contraction map, which means 2 properties. Number 1, it's a self map. So that means if you take a ball of radius r in this function space, and you choose a velocity inside this ball, and you apply this map, then the value of phi corresponding to that u is again back in the same ball. So if you repeatedly keep doing this, you will never leave that ball. You'll continue staying in there, okay? And the next property, that's called a self-map. The next property is a contraction. This means that if you take two velocities separated by some distance within this ball, and you apply the map, the phi map on them, the resulting values, phi of each of these velocities, they are closer than the original velocities are. So these two properties mean that this map keeps getting closer and closer to its previous iterates, and it will continue to stay in the ball. So eventually it's going to converge to a solution. And that's how we show the existence of solutions. We do the same thing. Now, all this was done for a fixed US here, right? We do the same kind of analysis for another map psi of US, writing down a similar equation for US with a fixed UN. And so jumping between these two equations during the iteration process will lead us to the final solution. Then eventually we bootstrap for a maximal time, T star. So that means we show that there exists some time T star greater than 0, but could be infinity, okay? But there exists some time T star such that as you approach T star, this particular norm for each of the velocities will blow up, okay, if T star is finite. So this gives us a local in time solution because we've shown that for some, there exists a T star where until which these solutions are well posed. Next, we want to extend this to global well posedness. So which means we have to show that this norm never blows up. And because our condition was that they should blow up if it reaches T star, therefore T star must be infinity. Okay, that's the argument by contradiction there. So we set up this inequality called the Grunwald's inequality, which is perhaps the most used in PDE theory. So if you have some quantity x, some positive quantity x, and you have this inequality dx by dt is less than k times x, then you can bound x through this exponential bound as long as k is integrable. And in fact, it turns out that this holds even if there is a logarithmic factor that corrects it. So even if you have x log x, that is still good enough for you to be able to bound. You just get a double exponential bound. And this is important here. So we set up what looks like an energy estimate, except instead of the L2 norm being the kinetic energy, we set up this higher order energy in the HM norm. And you notice this looks exactly like this first equation. dx by dt is less than x times something. So our goal is to show that this something is integrable. And here we use the Beal-Kato-Maeda potential theory estimate, which allows us to replace the gradient u in L infinity norm by quantities that we can better control, which is the entropy, omega and L2, and also omega and L infinity. But the price to pay here is this logarithmic factor. But that doesn't matter because even if there's a logarithmic correction, it still holds. So once we do this and plug this into this equation here, we can then show that this norm here, which is our x, is bounded for any time t, which means the solutions exist for globally in time. Okay. So this is a global well-posedness result from this HVBK model. Now, there are some interesting problems to work on in the future with this model, and I want to discuss some of them. So the first point here is this inviscid case that some of you have already raised. So we know that the Euler equations, which are inviscid, are well posed globally in 2 dimensions, right? But here we believe that if you make the superfluid viscosity 0, then firstly, this analysis won't hold because then the calculations here depend inversely on the viscosity. So if you send nu s to 0, things will blow up. So this method, this analysis itself won't work. But the problem here is that if you just go back to the model, this advective nonlinearity, which is the main nonlinearity to deal with in the Euler equation, can be written in a conservative form, which is a divergence of u tensor u. So that kind of gives you some level of symmetry in that nonlinearity, that it's u and u. The nonlinearity from the coupling term here also looks a bit like this, in that there's a gradient of a velocity and then there is a velocity. But you can't express this in a conservative form, like the advective nonlinearity. And that would lead to problems in the proof used for the general proof used for the Euler equations. So we believe that system may be ill-posed, and that is definitely something worth exploring in the future. Of course, we considered the 2D model, but if you look at the HVBK in 3D, in 3 dimensions, then you have terms relating to vortex filaments or the vorticity being bent, and that causes some forces. That leads to some forces. So, and again, the expression for that can also perhaps lead to the system being ill-posed, because it depends on like a product of the vorticity and the gradient of the vorticity. So it's a really higher order term. It's not the same as the advective nonlinearity. Finally, we can also look at the stochastic version of these equations, perhaps, to ask what happens if you stochastically force the normal fluid. How does a superfluid behave? How does the energy distribution change between the two fluids? Right? There are several questions that one could discuss in the stochastic case. Okay, so this was all a discussion on a large-scale model with the with the HVBK, where both fluids are classical, and we've assumed them to be modeled using a Navier-Stokes type equation. Next, I'm going to move on to a small scale, a micro scale model. This is called the Pitevsky model. It was derived in 1959. So here, the superfluid is described by the Schrodinger equation, the nonlinear Schrodinger equation, right? So this, and this is just the regular cubic nonlinear Schrodinger equation. This is a coupling term that couples the two systems. We assume the normal fluid, which is just called U here, is divergence free, but it's what's called an inhomogeneous incompressible equation. So it's incompressible, but the density can change from place to place, so it's inhomogeneous, right? This is the regular momentum equation. And so you notice that there are coupling terms to both the continuity equation and the momentum equation, right? And this term here is what is the biggest hurdle in the analysis of this system. We look at this system on a closed bounded domain with a smooth boundary in 3 dimensions. So we have to impose boundary conditions, right? The usual boundary conditions for Navier-Stokes are that the velocity vanishes on the boundary. Now here, because of this source term here in the continuity equation, we've had to look at the system at a rather high order of regularity. We've had to derive estimates of higher order, and that has forced us, for technical reasons, to impose this extra boundary condition that the gradient also vanishes. Now, one may ask, how do you impose this when you have a Laplacian? So what we do is we treat the Laplacian as a fractional power of a higher order operator. And the higher order operator's eigenfunctions are used as a set of basis functions. And that allows us to impose both these boundary conditions. Okay. Similarly, again, in order to derive higher order estimates, we need certain boundary terms to vanish, which I'll discuss shortly. We have to impose these extra boundary conditions on the wave function. And so once again, we deal with the Laplacian here as being a fractional power of a higher order operator. So the features of this model are, firstly, it's a non-linearly coupled model. You can see that B here is nonlinear coupling. The coupling is like relative kinetic energy plus some self energy. So if you recall, in quantum mechanics, minus I h bar gradient is the momentum operator. In classical mechanics, m times u is the momentum operator. So if you take h bar and m to be 1, then this is the difference of the momentum of the two fluids. You square it and divide by 2 times m. That gives you a relative kinetic energy. And this is just the self-interaction of the superfluid with itself. Okay. Right. So this is a this is a model that is bidirectionally coupled and allows for mass and momentum transfer, as you can see here and here. Right. The continuity equation has a sign indefinite source term. This quantity is sign indefinite. If you integrate it over the entire domain, then it's non-negative, which basically means that with time, the overall normal fluid will not decrease. The mass of the normal fluid inside the domain will not decrease. We've assumed divergence-free velocity and cubic self-interactions, right? And we've imposed the extra boundary conditions.
You said it was non-negative. Does that mean it could be positive?
It can be, yeah. It's greater than or equal to 0 when you integrate it over the domain. So that means that this is essentially a relaxation mechanism, the B term, So the superfluid relaxes and some of it keeps getting converted into the normal fluid.
Oh, I see.
So that's why,
it's the conversion back.
yeah, exactly. But we don't know what its sign is at any given point.
Well, it exchanges both momentum and mass.
Yes, momentum and mass, yes. Okay, so we set out to look for weak solutions to this model. And by weak, we mean that we choose some very smooth or sufficiently smooth test functions, right? We multiply the governing equations by the test functions and integrate by parts so that the derivatives are transferred from the the fields that we have onto these test functions. So that, which means the fields can be a little less smooth. You don't require as much regularity. And we call a triplet psi, u, and rho to be a weak solution to the Pitevsky model if they have this regularity and they satisfy the governing equations in the sense of distribution. So what I just said, that you multiply by a test function and integrate by parts. I'm going to clarify this notation. So, and for this, this is the integral formulation. I'm not going to dwell too long on this, but the most important thing here is the initial conditions are in h0 5/2 plus delta, u0 in this, and rho 0 is bounded in L infinity. Now, let me explain what this is. We choose delta to be a small quantity between 0 and a half. So what h 5/2 plus delta means that there is 2.5 plus a little bit amount of derivatives of psi 0 in L2 that are square integrable. 1.5 plus a little bit derivatives of the velocity are square integrable, right? The 0 here just imposes the boundary conditions. The D means that both boundary conditions are imposed and it's divergence free. It's a subspace of this h 3/2 plus delta that's divergence free. Okay. Just to put things in perspective, the NLS, nonlinear Schrodinger equation, has been studied a lot in mathematical literature before, right? It's been used to model dipolar quantum gases by including a non-local potential. It has a hydrodynamic formulation known as quantum hydrodynamics, QHD, which you can obtain by basically writing the wave function as a magnitude times the exponential of a complex number, a complex phase, and then you can separate out a continuity equation and a momentum equation. So it also gives rise to a very nasty pressure, quantum pressure term. But this system has been analyzed for strong solutions, so very smooth solutions by several authors. The QHD type models have also been looked at for weak solutions. Now, the inhomogeneous incompressible Navier-Stokes that we're considering, that also has a long history. Its first analysis was performed all the way in 74 by Kazikov, who first showed local in time weak solutions, okay? But assuming that the density is bounded below by a positive number. This was improved by Kim a few years later to allow for vacuum states, so where the density could actually vanish. Local strong solutions were for bounded densities, bounded below, were shown by the famous mathematician Ladyszenskaya. And more recently, local strong solutions have also been allowed to permit vacuum states as long as the initial conditions satisfy some compatibility criteria. Okay. Now, differences and similarities, just to compare with other works. This just means to the best of our knowledge. This is the first investigation of a bidirectionally coupled NLS-NSE model. Okay, the paper I mentioned before by Antonelli and Marcati did look at an NSE that coupled with NLS, but it was unidirectional. So they had a compressible Navier-Stokes system, but that was not affected by the wave function. It was coupled to the NLS. So the wave function equation would be dependent on the velocity, but you can solve this independently. So it was essentially like solving a more nonlinear NLS. Okay. And they obviously didn't have any source term for the density as well because the NSE was independent. Our analysis is most closely related to Kim's work, but we assume that the density is bounded below because we have to deal again with the source term, and more on that in a bit. Our initial conditions are more regular than the weak solutions that Kim showed, but less regular than the strong solutions constructed by others. And we have these higher order boundary conditions, which dictate our choice of the basis functions and the operators that we use for the semi-Galerkin scheme. Okay. Now, I want to state the theorem of existence, and then go through, again, a quick proof, the sketch of the proof to explain how we approach the idea. So again, we fix a delta between 0 and 0.5. We take our initial conditions. The density is assumed to be bounded below by a positive quantity, small m, and above by a capital M, right? Then there exists a certain time t, right? And a weak solution, psi u rho, which has this set of regularity for the wave function velocity and density. And these fields also satisfy an energy balance condition, the energy equation. Now, this time t is local. We've only been able to show local not local existence of solutions, not well-posedness. We'll get to that in a bit. Also, you may notice that the wave function and velocity are actually strong solutions, which is true. Based on the estimates we made, we actually ended up with strong solutions for the velocity and the wave function, but weak for the density. And that's why I just said weak solutions, because at least one of them is weak. So what's the strategy to establish this existence, right? First thing to notice, the density is not purely transported like it is for the general inhomogeneous incompressible Navier-Stokes. So because of that source term, we are forced to limit our evolution time to when the minimum value of the density reaches a prescribed minimum, epsilon. So we know that our initial density started with a lower bound of m. We choose some epsilon between 0 and m and stop the simulation, right? As soon as the density anywhere in the domain reaches epsilon. So that leads us to get only local in time solutions. So along following the Lagrangian path of the flow, we can write down this characteristic solution for the density equation. And because the initial density here is bounded by small m, and we require that the density is bounded by epsilon later on, it is sufficient if this source term here, this quantity, is bounded by m minus epsilon. In fact, an even stronger sufficiency condition, not necessary, but sufficiency, is that the absolute value of the integrand when integrated is bounded by m minus epsilon. Further stronger is the sufficiency that just by using a Holder inequality, like a generalization of Cauchy-Schwarz, we can state that if we can find a time t such that this t to the half times psi in the L infinity norm times b psi, where b is the operator, the coupling operator, in L2 L infinity is less than m minus epsilon, then that is the time, the local existence time. Okay. So this is our goal here, to show this, to find solutions that satisfy this. Our modus operandi is to derive a priori estimates first, and then construct approximate solutions to a set of approximate equations. And then we pass to the limit in the approximations. And again, when we take the limit, what we approach will become our final solution, just like before. Okay.
I have a question.
Yes.
What is the size of the spatial domain? It seems that
it's a bounded domain. It's a bounded domain with a smooth boundary. So just anything finite.
So do you end up playing with the size of the domain to get these estimates? Because it seems you could put the problems far enough away in a very large domain.
Right. The size of the domain does come up in some of the estimates. It does.
Okay.
So this is for this is valid for a bounded domain. Yes.
Mm-hmm. Thanks.
So one final jump of sufficiency is, because it's difficult to deal with the bounded L infinity space, is the fact that the L infinity norm in 3 dimensions can be bounded by a little better than 3/2 in the Sobolev space norm, right? So, and this is where this requirement of all these deltas that we saw earlier comes in. A little bit better than 3/2, a little bit better than 5/2, and all that. So we have to try and control this norm. And the way we come up with some estimate or control for this is we take the NLS, we act upon it by minus Laplacian to the power s, where s is some sufficiently high power of derivative of a derivative order, right? We choose s so that we end up with this norm basically. And then for this quantity minus Laplacian s psi, we calculate like an energy estimate. So we multiply by the conjugate of that and take the real parts and do an energy balance. In doing so, we look at this term, and we want this term to vanish, right? Because this is a much higher order derivative term because of the presence of the Laplacian. So we need to integrate this by parts, and that leads to a boundary term that vanishes. And that integration by parts is where we need all of the extra boundary conditions for the wave function. So this is a justification for why we needed to add that. Okay. Now, similarly, if we're going to control B in this space, h3/2 plus a little, because B contains U and U square in the coupling, we need to control U also in the same spaces, h3/2 plus a little bit. And the way we achieve this, the estimates in Kim's work are not sufficient to give us these bounds here. We don't get L2 bounds, we get like L4 bounds in time. So that's not enough for us. So we approach this differently. We use a technical lemma called the Liouville lemma, right? Which requires that the velocity and its time derivative exist in dual spaces. So the velocity is in hs, 0, and the time derivative is in h minus s. And because we need s to be 3/2 plus delta, and we impose this h0s, that means that on the boundary, both the velocity and its derivative need to vanish. So this is the reason for requiring that the extra boundary condition for the velocity. Okay. So now that we've justified where these boundary conditions are coming from, how do we actually impose them? Okay. So for the velocity, can everyone hear me?
I can hear you. You disappeared for a moment.
Yeah, the little mic wasn't working. Yeah. Now
Okay,
I feel like a stand-up comedian. So, okay, we consider this problem that looks like a Stokes problem in the regular Navier-Stokes theory, right? The Stokes problem is without the 2. So it's just minus Laplacian V plus gradient P is equal to F. F is some known field, a source term, which is divergence free. V is divergence free. And normally we have just V equal to 0 on the boundary. But here, since we have a higher order Laplacian, we can impose the next boundary condition too. And if we use a Leray projector, which removes all gradient terms and projects onto the subspace of divergence-free functions, then we get rid of this term. And this Leray projector times minus Laplacian square, we call the by-Stokes operator, because it's like the Stokes operator with power 2. Okay. We can show that this eigenvalue, this operator here has discrete, strictly positive, and non-decreasing eigenvalue spectrum. And most importantly, it has a sequence of divergence-free eigenvectors, which are smooth in the domain, orthonormal in L2, and orthogonal in H2. So we use this sequence of eigenfunctions A sub j to form a finite dimensional linear combination with some time-dependent coefficients. And this becomes our approximate velocity. And because this has the required boundary conditions, this would also have the required boundary conditions. Okay, this is how we impose the extra boundary condition for the velocity. We do a similar thing for the wave function. In order to satisfy all the estimates that we need, all the boundary conditions, we take a sufficiently higher order Laplacian. So we take what we call the penta-Laplacian operator here. And again, this has a set of eigenfunctions B sub j. So we form this finite dimensional linear combination, right, of with complex valued coefficients, time-dependent coefficients. And this is an approximate wave function which satisfies all the boundary conditions we need. Okay. Next, we have to make sure that the initial values, the initial data, also are have this finite dimensional form. So what we do is we project the U0 and psi0 using these projectors onto the space spanned by the first n eigenfunctions of the by-Stokes operator and the penta-Laplacian. So this gives us our approximate initial conditions. We have to make sure that as n goes to infinity, this approximation actually returns back to the original wave function and velocity. That's rather straightforward to show for this projector Qn, that it converges to the identity. For the velocity, because of the presence of the Leray projector, it's more technical. There are a lot more calculations to do, but it can be done, and we show that holds. Finally, the last element is the initial conditions on the density. And here we use a modifier to come up with a sequence of initial densities that are smooth and converge onto the initial density in L2 as n goes to infinity. And it's also bounded by the same lower and upper bounds. So now the problem with a modifier is whenever you modify in a domain, you have to peel off a little bit at the end of the domain for when you define a modified function. So in order to allow room for that, we expand the domain by just extending it by some unit distance outwards and define this new field ρ0 tilde, which is equal to ρ0 here and equal to the lowest value m in the annular region. And because we have this annular region, we now have room to strip a little bit off the edges. And that gives us a modified function defined within the domain omega 1. And just taking its values within this inner domain that's of interest, we get the smooth approximate initial densities that we're looking for. And by the properties of the modifiers, we can verify all of these conditions. Okay. So now that we have our semi-Galerkin basis, we have our approximate initial conditions for all the fields. The next thing is to write down approximate equations. So we set up this approximate system here. We plug in all that finite dimensional expansions into this and write down equations for the time derivative of those time-dependent coefficients. And we solve those ODEs in time that are functions of time, basically using another contraction mapping argument, just like before in the HVBK case. And we show that there exist solutions to this approximate system. And then we pass n to go to infinity to the limit, and whatever they converge to, that becomes our final solution. So that's how we construct solutions to the Pitevsky model. Okay. But now that we've constructed solutions, the next question is, are they unique? Can we say anything about the uniqueness? Now, weak solutions generally don't have enough regularity for us to do the uniqueness calculations. So we usually cannot comment anything about their uniqueness. And in some cases, they've even been shown to spectacularly fail. An exception is the 2D Navier-Stokes that has global in time unique weak solutions. So a cheat code here, so to speak, is weak strong uniqueness, where we say, okay, we start from a certain set of initial conditions and we've constructed weak solutions. Let's assume that there is a strong solution starting from this same data, right? So if that is the case, then we can show that both the weak and the strong solution are the same. So that's called weak strong uniqueness. This has been done by several people in various problems, many variations of Navier-Stokes, including Professor Mele here in the audience. But the usual argument used for weak strong uniqueness, that doesn't work here, or at least doesn't appear to work for the Pitevsky model because of our various coupling terms. So we explain why that doesn't seem to work, and then motivate the search for a related but different result, where we take slightly less weak solutions, and then we prove something called a weak moderate uniqueness result. Okay. So this is the conjecture that for the weak strong uniqueness. So here we take really weak solutions. So not the ones that we constructed, but really weak ones, where the regularity of these fields is defined only by the energy balance. And so for instance, the velocity is only in L2, right? Because kinetic energy, and the superfluid mass balance, okay? Only these conditions tell you what these fields should look like. If you consider such weak solutions, and you assume that there exists a strong solution from the same data, and by strong, I mean that solution has this regularity plus some additional regularity on the density and velocity, then the solutions are identical. So this is usually the statement of weak strong uniqueness. Now, I want to draw your attention to the fact that the strong solution here is actually pretty smooth, in the sense that this velocity, it's in this space W1 infinity, which means its first spatial derivative is bounded, is in L infinity. So it's pretty smooth in that sense. The time derivative is also in L infinity. So these derivatives are bounded, so they're rather smooth solutions for what we consider strong here. But this doesn't work because the weak solutions are so weak here that we cannot handle the coupling terms, all the nonlinear interactions that are through that B operator. So instead, what we do is, let me explain a hierarchy of solutions here. What we constructed earlier in the previous section, I'm going to call them for now as strong, strong, weak solutions. Strong in wave function, strong in velocity, weak in density, right? What I just explained in the previous slide are really weak solutions governed by just this energy balance and mass bound. We attempted to show weak, strong uniqueness. So we go all the way down to really strong solutions, very smooth velocity and density. And with that, we tried to couple the weak and strong and try to show a uniqueness theorem. And we don't think that that works. So what can we do? So what we do is we move a little bit down this ladder and look at less weak solutions. So these are one order of derivative better than the weak solutions from here. Okay. So the velocity and wave function are one order of derivative better. And now for these less weak solutions, we can certainly show less weak, strong uniqueness. But we can actually do better because these have a little better regularity. We can even bring this up the ladder and define moderate solutions, which are less regular than these very smooth solutions, and show a less weak, moderate uniqueness. Okay, so I hope this gives some idea of what's coming next. So now we consider a less weak solution. So you noticed earlier the wave function was in H1, now it's in H2. Velocity was in L2, which is H0, but now it's in H1. So it's gone up by one derivative. The density is still the same. Now we assume that there exists a moderate solution from the same data, right? And the moderate solution has this regularity, plus it has the density being the same as the strong solution case, but you don't require this on the velocity field. And the time derivative of the velocity does not have to be in L infinity. It's way weaker. It's in L3. So it's cubic integrable. So if we consider such a moderate solution, then one can show that this less weak and moderate solutions are actually identical. Okay. The proof of that is by using the energy structure of the system. We subtract the equations for the less weak and the moderate solutions, and then set up, again, a Grunwald's inequality. So you have d dt of something is less than some integrable function times the same thing. And because this is integrable, we show that for as long as these solutions exist, they must be unique, since the initial condition of this quantity is 0, right? They all start from the same data. So this difference is 0, this is 0, this is 0 initially, and their rate of change is bounded by a linear function. So they must remain 0 for as long as they exist. Okay, so this is our uniqueness result for the Pitevsky model. This model also has a lot of open questions that have arisen, that have come to my mind while doing all of this analysis. First thing is, can we do anything about global solutions? So as I said, the local solutions requirement was because we had to stop the simulation of this system when the density reached a certain lower bound, epsilon, a prescribed lower bound. Can we do away with that? Okay. Can we deal with the continuity equation in any better way? So, and related to that is this question of extra boundary conditions. So just tracing our path back, we needed extra boundary conditions to deal with the integration by parts. We needed integration by parts to deal with the higher order estimates. And we needed the higher order estimates because we needed B psi to be in some higher order space. And that was because we had to deal with the source term in the way we did. We couldn't come up with any other better way to deal with it. And I couldn't find any models in the literature that had this nature of source term, that is sign indefinite. So that leaves the open question, is there a better way to deal with the source term so that we don't need to do all these higher order estimates and go down this path and end up with these extra boundary conditions? Okay. Lastly, can we allow for vacuum states? So can we extend our analysis to allow for the density to be 0 at some point? And if we're able to do that, that's useful because then we can actually extend our results to the whole space too. Okay. And of course, what we considered the Pitevsky model I showed you was a slight simplification of the original model. Pitevsky's derivation had a fully compressible system with thermal effects, an entropy equation, and whatnot. It's much, much more complicated. So if one is really adventurous, then maybe that is something worth looking at too. Okay, so this is the work that I've done, and this has not been alone. So I want to thank a lot of people, take a couple of minutes. Firstly, to my advisor, Konstantina. yeah, thank you very much for mentoring me. You've been an amazing mentor, an amazing advisor. I've learned a lot of mathematics, PDEs from you in various ways. Your course, TAing for you, and of course, working with you. So this is a picture from almost 4 years ago when I ascended to candidacy. So I want to thank my committee members. Professor Dorland, who's on Zoom, Professor Drake, Larson, and Lathrop, who are here. Thank you very much for agreeing to be on this committee, taking the time to read my thesis, and I look forward to your comments. There are several math and physics professors in the departments here who have really helped me and made and really inspired me, and I consider them very good influences in my life. Jacob Bedrosian, Professor Dave Livermore, Professor Mate Macadon, Professor Mele, who's here in the audience, Professor Niranjan Ramachandran, who is not a fluid dynamicist, but he's definitely been a great mentor and given me a lot of good advice on how to navigate grad school. Professor Victor Yakovenko in the physics department, and many, many others. I want to thank all my fellow grad students and the postdocs that I've interacted with, some of whom are on the Zoom call, I think. So thank you for all your very enriching discussions. They've helped me gain a better perspective of my own work at several junctures when I was stuck. There is obviously a lot of bureaucracy to deal with in any enterprise, UMD included. So a big thanks to all the staff members here who have been very, very helpful to get through all the paperwork, especially as an international student. I also want to make a quick shout out to all my professors at my undergrad institution, IIT Madras, who have the first three are physics professors who really, through their courses and the interaction and the research I did with them, made me want to pursue a career in pure sciences and in mathematics. Professor Venkatratnam, also a mechanical engineering professor that I worked with there, is perhaps my biggest academic influence in my life. So I want to thank him. Thanks to all my friends. Some of these are really old photos. I think this is from over a decade ago. So we couldn't get a better picture, but thanks to all my friends who helped me, especially through the last 2 years with the pandemic and being locked down. This was very, very hard. And yeah, finally, thanks to my family. They've been a great support system throughout. This is perhaps the only picture with all 7 of us, 3 humans, 3 dogs, and me. So yeah, and even in that, I think I don't have a smile. So, but anyway, so with that, I just want to show some references, and thank you very much for all your time and support. And I'm ready to take questions, both from Zoom and from the audience here.
The math world, we first invite the general questions, and we can also ask general questions, and subsequently we let the audience go, and we drill a little bit more with time. Okay, yes.
I'm trying to see if I can unmute everybody.
So,
Okay, I have allowed people to unmute. I have allowed people to unmute themselves. So if anybody has questions in the among those on Zooms, and please feel free to unmute and ask away. Any questions from the audience here? Well, the fewer the better for me, I guess. So okay.
say something about your general plans for this project.
Oh, yeah. So I have the theme of my research here at UMD has been mostly looking at asking the good questions, well-posedness and stuff. So I am more interested in going forward to look at ill-posedness. So looking at the HVBK model when it's inviscid, right? That is something I'm really looking forward to doing and trying to show ill-posedness for that, hopefully during my postdoc. But yeah, that is one thing. And I've also been, Konstantina and I have been working a little bit on some stochastic compressible Navier-Stokes, trying to look for invariant measures. So that is an ongoing project. We couldn't complete it. It's a much harder problem than we originally thought it would be. So we couldn't complete it in time to include it here, but hopefully we can do that over the summer and get something. Yes.
My bias is that I like simulations. So could any simulations be useful for this or helpful?
Well, the HBBK model has been simulated a lot. It's been used by various simplifications have been used. The Pitevsky model has not been simulated in full, as in both its the NLS and NSE. What has been done is they fix a certain normal fluid velocity that arises in the Pitevsky equations. Let me go back all the way. Right, so you fix the velocity here. So you don't solve a Navier-Stokes problem. You just fix the velocity and then use that as a drag term and then just simulate the wave function. That has been simulated. But as far as I know, I don't think anyone has done a full simulation of this system, and even this reduced system with the divergence-free condition. So it would definitely help doing simulations of this to see what one could perhaps expect. Because like if you see blow up happening during a simulation, then you would also want to perhaps look for blow up in analysis while you're actually theoretically analyzing the model. Yeah, so that is of interest. Oh, I don't know if it's questions or comments. Oh, yes, that's my father, who's also a fluid dynamics person. He's a chemical engineer. So why do you want the density to go to 0? Should it be vanishingly small? Do you want or need it to approach low value smoothly? Density going to 0 is just that there is, let's say, like a bubble within the fluid. So we're not wanting it to go to 0, but if it goes to 0, what happens? Can that be handled? Then usually in weak solutions, you can handle the density going to 0. That's possible. For the strong solutions, like I said earlier, let me move this away. So for the strong solutions, dealing with vacuum states, which is the last point on the slideshow here, requires some additional compatibility criteria on the initial data. Otherwise, there's been no other way to deal with vacuum. The reason we want to allow for vacuum states in looking for weak solutions is because if we allow rho to become 0, then we can just consider this bounded domain as actually an unbounded domain with density 0 everywhere, except within this region of the domain. And so then we can actually use these estimates to extend the results into the entire space R3 instead of having to deal with just a fixed domain. So that's the reason to allow density, allow vacuum states.
What is the next question? There was 2 comments.
Oh. Do you want or need it to approach low values smoothly? That depends on what kind of, so how smoothly it goes depends on the regularity of the density function itself. So if your density is just L infinity, then you can't comment anything about it. If it's just bounded, you can't say how smoothly it's going to vary or not. Yeah, so it depends on the regularity of the solutions you construct.
Probably one more if you scroll up.
Oh, thank you, Jacob. And thank you to everyone else on the talk too. So are there any other questions?